So good afternoon to everyone. I don't know if there are chair, but if you want, we can just start. I'm a technical assistant. I'm Simone Corrado, and I'm informed that 4 presenters out of 5 are here. Yes. It's a 5. Okay. Yes. And I think we can start without chair, and if they just arrived, meet. Okay, so the first presenter is Ilias Karlautoglu. Sorry for my English. And we present a paper entitled "An Empirical Comparison on Transform-Based Models in Vulnerability Prediction." So the stage is yours, and this is your presentation. Yes.
You start the same screen.
Yeah. Okay. Okay, so the stage is yours.
Hello all, my name is Ilias Karlautoglu, and I'm a PhD student in the University of Macedonia and the research associate in the Center of Research and Technology Hellas in Thessaloniki. And I'm going to present you now our paper entitled "An Empirical Comparison of Transformer-Based Models in Vulnerability Prediction." Nowadays, software security is considered a very crucial aspect of software quality and is a very important part of the software development life cycle, since more and more software enterprises are looking to provide their customers with secure and dependable software. The most important threat of software security is the existence of vulnerabilities in the source code, and a mechanism that can deal with the early identification of vulnerabilities in the code is called vulnerability prediction, which is commonly performed using machine learning models that are trained or label vulnerability-related datasets and learn to classify the software components as vulnerable and non-vulnerable. In this slide, we give you an overview of the vulnerability prediction mechanism. The source code of the dataset is given as an input, and we extract software attributes that are fed in the machine learning model, and in several machine learning models in order to find the optimal one. And then in the execution phase, when new software arrives, we extract the features and we fed the already trained vulnerability predictor in order to make a prediction for the existence of vulnerabilities or not. The vulnerability prediction mechanism using text mining as our model is illustrated in the top figure. We receive source code, we tokenize it, creating sequence of tokens. We encode each token with embedding vectors, which are the actual input of the machine learning model or the deep learning model. And then this model outputs vulnerability flags that can take two values, either 1 for the vulnerable components or 0 for the clean components. And the sigmoid output is the likelihood for the component to be vulnerable. In the second figure, you can see the vulnerability prediction as a tool in practice where we want to analyze the software project, we tokenize the source code, we feed the source code to the deep learning predictor, and the predictor outputs a vulnerability prediction report. In the literature, initial vulnerability prediction studies examine the software metrics that are extracted statically by static code analyzers, and they are the input of machine learning models. Later, studies back with text mining appear, and they prove to be superior than the software metric-based ones. First text mining studies employed the technique called back-of-words, while later studies represent the source code as sequence of tokens. In these studies, use word-embedded techniques to encode the meaning and the syntax of the words in the source code. Recently, some studies have started to examine the graph embedding of source code after representing the code in a graphical format. In this slide, you can have a view of the text mining-based representation of the source code. In the top, you can see the barcode, where the source code of which component is represented by the words that it contains, the token that it contains, and each token is accompanied with the number of occurrences in the source code. In the middle, you can see a table of a sequence of tokens, where each component is a sequence of all its words in the same order as they appear in the actual code. And in the bottom of the slide, there is a graphical representation, in particular a code property graph, where a software method is represented in a graphical format. In our study, we consider vulnerability prediction as a task of source code classification between valuable and non-valuable components, and we consider also source code classification as a task of natural language processing. So we take advantage of the recent advances in the natural language processing field with the transformer architecture that has arrived, and we take advantage of the LLMs, which means large language models that have been training huge corpuses and have obtained language understanding. So we investigate the efficiency of LLMs in vulnerability prediction, and in particular, we compared several transformer-based language models by fine-tuning them in the downstream task of vulnerability prediction. The transformer model has revolutionized the NLP field, having demonstrated impressive performance on various tasks, such as text generation, question answering, text summarization, and its main power over the recurrent neural networks and the convolutional neural networks that are considered the state-of-the-art models for learning sequential data is the fact that transformer can process the whole input in parallel and does not rely on any sequential processing. The transformer model also assigns different weights to different words in the input sequence based on their relevance to each other, and therefore it can capture long-term dependencies between words in a better manner than the current neural networks. It also uses positional encoding to preserve the order of words in the input sequence and learn information about the position of each word in the text, such as the source code. The most famous one is probably the generative pre-trained transformer, or else GPT, which is provided by OpenAI, and it is a model pre-trained on predicting the next word in a sentence based on the context provided by the preceding words. Another popular transformer-based LLM is the bidirectional autoregressive transformer, or else BITE, which provided by Facebook AI. And during its training, some text is first corrupted using a noise function, and then a model learns to recreate the original text. Regarding BERT, which means bidirectional encoded representation for transformer, it is pre-trained on the mask language modeling objective, where some tokens of a text are masked, and the model learns to predict the actual words that are behind the mask. And there are also several BERT variants to improve the time and memory efficiency of the models, such as Roberta, DCBERT, Albert. And there is also a special case, which is CodeBERT. CodeBERT is a bimodal model that's dependent on pairs of natural language and programming language, and it actually has prior knowledge of 6 programming languages. For our implementation, we utilize the Hugging Face library, which is a great library that provides not only the architecture of several NLP models, but also their pre-trained weights and the model tokenizers. And in this table, we have a view of the size of each model and the number of parameters. For our dataset, we utilize GitHub as our basis, and a GitHub API-based tool searches several GitHub commits based on keyword combinations that are indicative of a vulnerability fix. For example, prevent DOS, fix vulnerability, fix buffer overflow. If we detect such commits, we keep it, and the parent version of this commit contains the vulnerability, while the latest version can be considered vulnerability free. So we have two folders, one with the vulnerable components and one with the non-vulnerable components. So our approach can be separated in three phases. The first one is the pre-training phase, where a large pre-training corpus is being preprocessed and tokenized, and is fed to a transformer-based model in order to obtain the context-aware embeddings. And then during the fine-tuning, we utilize the aforementioned training dataset. We extract a subcode of Python files, we preprocess them and tokenize them, and we fed the transformer-based model and fine-tune it along with the classification layer in the top of it in order to make it to learn to classify source code as vulnerable or not. And in the execution phase, which is the testing phase, we utilize a separate part of our dataset, which is totally unseen. And during the same process, we fed a vulnerability predictor in order to make predictions. We have to note that in the preprocessing step, we removed all comments and empty lines, and we replaced string literals and numerical constants with specific tokens because we consider them as non-indicative of vulnerability. And then we convert the source code into a list of sequence of tokens. In training and evaluation process, we separate the dataset into three parts: the training one, the validation, and the testing set. And we fine-tune the model into the training, and using the validation set, we choose the best hyperparameter set, as you can see in the table, which is the best model. And then we train on training and validation sets combined and test it on the totally unseen testing data. To evaluate our approach, we utilize common classification metrics such as accuracy, precision, recall, and TEV scores. But we consider as most important the F2 score because it considers both precision and recall, so both true positive and both false positive, but it gives a larger weight to the recall because in a security task, it is more important to identify as many risks as possible rather than having some more false positives. In this step, you can see the empirical comparisons of the transformer-based models. It is clear that in every classification metric, we have CodeBert as the best one, especially the F2 score. And we can see also that most of them, especially the BERT-based ones, can make quite efficient predictions. So, the main observations are that CodeBert proved to be the best one, and also that the BERT achieves better results than GPT and BART in this specific task. So, the results highlight the capabilities of those models to be adopted in the task of vulnerability prediction, and secondly, and most importantly, the results highlight the importance of injecting programming language knowledge into the pre-training phase. And this is why CodeBert seems to be superior than the others. In our future work, we need to investigate whether prior knowledge on natural language for programming language-based tasks is beneficial to these models, or it would be better to pre-train from scratch only on programming language, a transformer-based model. So, in our future work, we will pre-train from scratch those transformer models, both using natural language and programming language, and then using only programming language in order to see if natural language is noise or a model based only on programming language source code is a better option. Thank you very much. I will be happy to answer your questions.
So thank you, yes, very good presentation. And there are any questions from the audience? So, your question is, okay, thank you. Yes. We can go with the second presenter, that is Willy Shaper, and presenting embedding visual software analytics on GitHub platform on the example of static search code, metric, and software maps. So, which presentation is here?
The last one.
The last one? Okay. Okay, so let's put it here.
Thank you. Yeah. Welcome everybody on my talk embedding visual software analytics on the GitHub platform on the example of static source code metrics and software maps. This is a work of Willy Scheibel and some of his co-authors. My name is Daniel Atzberger, and today I will present this to you. So first, let me give you a short explanation what software analytics actually means. And there's a popular cited definition by Zhang et al., which say that software analytics aims to obtain insightful and actionable information from software artifacts that help practitioners accomplish tasks related to software development, systems, and users. So this definition contains many things. First of all, what are those software artifacts? Here on this figure, you see a typical software development cycle, starting from a customer who explains his problem, and then a domain expert who specifies requirements, which result in tickets that describe certain features or tasks in general, that are then implemented and tested and evaluated. In every stage, different data is generated. For example, when the developer pushed their code into the version control system, each commit is stored and can be analyzed by, for example, machine learning techniques as shown in the previous talk. And in our talk today, we will deal with the special case of software metrics, which measure certain aspects related to the complexity or quality of software, of source code in particular. We also restricted our attention on GitHub. GitHub is the most widely used and most popular social coding platform worldwide. In 2022, it contains 61 million It contains 61 million repositories, which also include very popular projects like the Mozilla Firefox browser, all those cryptocurrencies like Bitcoin, and widely used machine learning libraries like TensorFlow or scikit-learn. And there are actively 83 million developers who participate in some sort of open source project. The data from GitHub can be accessed using its API, the former REST API, or the novel GraphQL API. There are different commercial software analytics services around. Here you can see the front end of a company named Serene, which is based in Potsdam near Berlin. And it shows two things. First of all, on your left-hand side, it provides different measurements, for example, complexity improvements or some sort of measuring of productivity that are captured using the software metrics. I will explain it in some minutes. And on the right-hand side, you see this 3D visualization, which is a so-called tree map that we will also detail. And the idea is that by using visualization tools like this tree map, the user is supported in various program comprehension tasks. For example, here you see this red quad, which is pretty big and it's colored in red. So basically something strange is happening in that file. The problem statement that we wanted to address is that readily available software analytics tools are often operated as external services, which means that the customer produces the data and then gives it to the company, but the actual data is kept internal and no further use of the data is available. And what we did in our work is that we compute static software metrics on a per commit level and store it in the Git repository itself. We later use the GitHub API to load this data, which is stored as Git object, and feed it to some other service, like a visualization service. As we extend the basic GitHub CE pipeline, it was also relevant to measure the impact on the memory consumption and runtime performance. Our process can be divided into two parts. The first one captures the step 1, 2, and 3, and the second one 4 and 5. In the first step, when a developer commits a code, static source codes are computed as a GitHub action and then uploaded as a blob and then stored in a CSV file, which can then be loaded by another service in a browser, for example, for showing a tree map. Our analysis step is centered around the measurement of source code metrics. And as I already said, metrics somehow measure the quality or complexity of a source code on a file level or a more general source code entity like several file levels. And they all rely on parsing parts of the source code for regular expressions or counting some measurements like the lines of code, the number of comments, and derived numbers like the comment lines of code. In our considerations, we will use the following 5 software metrics, but there are many more. They are often used to create some sort of statistical model to locate defect-prone source code entities. So for example, if one software source code file shows extreme values in complexity values, it's more likely to contain defects than a very small file, which is mostly made out of comments, because I guess it cannot fail then. A common tool to visualize software metrics are so-called software maps. They provide a spatialization for software which has no intrinsic gestalt in that sense, in a cartographic metaphor, where each quad represents one source code file, and the quads are arranged to capture the hierarchical folder structure of the entire software project. And this 3D representation offers various visual attributes like the height or the color, the size of the area, and texture. You can also visualize dynamic transitions as animations. So that's why we decided to use this software maps as a visualization tool. In our experimental setup, we wanted to measure the effect on runtime and memory consumption. And for that, we investigated 8 open source projects that are all written in TypeScript. So the metrics, especially their parsing, somehow depends on their underlying language. And our 8 projects, they differ in the number of files and the number of lines of code. Our largest one is Visual Studio Code. Our smallest one is an internal project for providing the software analytics embedding. Another one, WebGL Operate, for example, is related to computer graphics, Angular for web development. So 8 different projects, all written in TypeScript. And our measurements showed that the memory impact and also the runtime effect depend linearly on the underlying number of files or lines of code, which is, I guess, very good. For example, if they would depend on some quadratic measure or something, it would be hard to integrate our pipeline into GitHub. However, our approach comes with some limitations. So although we focused on GitHub Actions and Git for our prototype, the approach is applicable for different development setups as well. However, we didn't extend it to something different. We just rely on GitHub. We also need to extend our approach to further languages and metrics. We just captured 5 very basic metrics, all for the TypeScript case. And another problem that is sometimes neglected is that there are also some security considerations that need to be undertaken, because software metrics, they measure the behavior of software developers, and in some countries it's not that allowed to measure some aspects. But however, to summarize, we proposed an approach to augment Git commits of GitHub projects with software analytics data on the example of TypeScript projects and static source code metrics. And we used this approach to visualize GitHub project using a basic React client. And the results are then showed as a tree map. In our future work, we want to address the security consideration and want to develop more metrics or include more metrics for different languages. That was my talk. Thanks for watching and listening. If you have any questions.
Thank you, Daniel. Sorry, and so thank you again. Instead, with the next presenter is Andreas Flipper with a paper entitled "Insights from Attention: New Approaches to Visualizing Transformer Model Output." Okay. Sure. Which one?
The first.
The first one. Okay. Yes. Just a second.
So, I'm Andreas Fricke from Hasso-Plattner Institute from the University of Potsdam in Germany. And my colleagues and I, so Raphael, Adrian, Billy, and our professor, Jürgen Döner, has dealt with the topic which is on vogue, let's say. So who has worked with ChatGPT, for example, in the last few days? I guess many of you, and we asked ourselves, how can we visualize what is happening behind this mystifying box, this black box? And so we, in the context of research seminar with students. Raphael is a student which participated in a seminar about explainable AI. Let's deal with the topic, how can we visualize these things, what are happening in the behind the curtain, let's say. So we asked ourselves for that, that the challenge of ChatGPT is it does something, but nobody knows how exactly it works. And we try to understand and find the parameters behind that, how we can reconstruct the process behind that, how we can understand how a procedure is taken, and we tried to put that into visual context because it's easier to communicate with visualizations than with parameters and so on. So we also use the transformer model. So we've heard about the technical specifications so far. I will go a little bit into detail, but just as on an abstract level, let's say. And we were trying to do to extract parameters from this box, visualizing these parameters, and has tried to make this a bit more structured to enable the user in the end to understand what is happening behind the curtain. So, as I mentioned, we are also focusing on the transformer model, and we are, as the title says, we are focusing on attention. Attention is a part of the transformer model, and we will try to use this parameter as a key fact of the transformer model, to use these parameters to visualize it for the end user in the end. So we have the fact that these transformer models are in kind of a hyperspace, so it's more or less very complex, and it's not so easy to even get the idea what is happening behind this models there. And if we are talking about hyperspace, then we have axes and we have points, and it's all kind of interwoven to each other, and we try to put some structure in that. That was the idea here. And for sure that, I guess it was on your slide, that with the transformer models, we can go parallelized, so it's much more convenient and performant than the simple linear structure. So, as I mentioned, we are focusing on the attention. You will see that in a moment, and we try to extract these values, parameters, importantly the attention, and try to visualize that at the end. So, what does the transformer? Maybe that's interesting because I do not know. It's very abstract here, but I put that slide into the presentation because I thought you should have an idea what exactly is done behind the curtain. So, at the first step, we have a sentence. In this case, the cat sleeps on the, and we are asking, okay, what's coming next? So we have to tokenize this. So the computer is doing nothing more than numerizing, tokenizing the words. So 1, 2, 3, 4, 5, for example. That's what the computer understands. So next, we have an embedding. So this hyperspace where we all have these words in interwoven structure, let's say. And then we try to find the position of each of these words. And then we are looking, okay, we have these words, and we are looking for nearest neighbors, let's say, in hyperspace. So, and that's the basic idea of how this transformer model works in the end. And then we are looking for parameters. What is the nearest word to that context? That is a value which we can use for calculation afterwards. Then we are doing some magic stuff. That's called here the fifth item. So weighting. That's not part of this talk, but that's also very important. And then we are looking for, okay, in the row we go step by step, starting with the, going to the cat, going to the cat sleeps, going to the cat sleeps on, and so on and so forth. So that's the 6th point here, it's context. And in the last but not least, we are knowing, because of the hyperspace de-risk world, it's bad, what we're looking for. So how does it look like? Briefly, we're going from 1, 2, 3, 4, 5, 6 to the end. As I mentioned, tokenizing, looking for the hyperspace, it's just 2 dimensions of the axis. We are seeing, okay, there might be a point in the hyperspace where different words appear at the same spot. So bad cat sleeps are somehow aggregated there. The value there is somehow at this point, our imagine that this might be a component which defines, for example, just an example, fluffiness. So they are grouped together. Then we are calculating all these values with each other. We are getting scores. That's actually what the AI is calculating in the end. We are using these scores, putting some basic masking stuff there, because we have here admittance metrics, but we just need the upper left side here because it's doubled there. That's the magic basically, because this softmax, which is now not the topic of this talk, but here's some magic, some weighting, some context weighting. Then we get results, and then we're doing this for all of the our key value pairs here. So as I mentioned, we start with the, then we have the cat, then we are looking for context, the cat sleeps, and the results, what we are seeing here, have been calculated before. That is the idea of what is happening behind the curtain. Abstract and easy and just in one slide. But we are doing this because we want to understand behind the curtain how these parameters are calculated, and we want to use these parameters, these attention parameters, to visualize in the end how the system, the model behind has done his or her or its decision, whatever. That's the idea. So that's somehow the magic, because it might be the case that we got several best fitting parameters with high values, low values, and then magic, as I said, behind the curtain, chooses maybe not the highest value, but the more context-aware value. So what we got in the end, we saw this before in your talk, we got a vocabulary, so the basic embedding stuff. We got the scores, what we have calculated before, and we got the output, what we have designed before. And this is also just output, but partial total here. Matrix calculations are very expensive, so there is some ongoing research on how we can design these calculations more optimized, more performant in the end. So it's the same structure as I mentioned before. This would be the cat sleeps, and then you would calculate the next word in this stuff. So just the dot product calculation. Yeah. So as I mentioned, it's about visualizing things, but this stuff before was to get an idea what we want to visualize. So we want to visualize the parameters, and our idea from the visualizing concept is demystifying this black box behind. I hope you got an idea what is happening behind. So we try to put these parameters into a specific layout for visualization purposes to get an idea what is happening behind the curtain, and more important, to it's called here retrospective or more introspective view on what is happening within the process. So one problem of AI or these large language models is that if you are doing the same process on a different machine or in a different model, you get a different answer. So it's not transferable, it's not reproducible, and we are trying to put some context here to enable the user to track where is what happening, and this is our idea how we do that. So you will see in a moment what this would look like, but more or less it's written here how we what we used for this visualization. We used a Java prototype. We used a graphical user interface in Java prototype. Used TensorFlow and Keras behind that. Some basic interaction techniques for zooming, panning, and so on. So low level, but the idea is to visualize the parameters and to get an idea what should be next. That is the focus of this work. And then we have nodes, we have edges for sure, and yeah, obviously it's a graph layout because we have a sequence in our sentence. So basically, we try to focus on context here, and I think it's more easy to see that. As I mentioned, it's just an idea. This work is just representing what can be done and where can be the next thing happen in terms of making AI explainable, and we choose, as I mentioned, the visualizing. So what you can see here abstractly is that, for example, we have the sequence here in the force-directed graph layout. We're starting here, that's the longer sequence, not the cat one, and starting here, it's ending there. And for example, at this point, we did a stop mark and wanted to see, okay, this word, for example, or maybe we choose another one. This one is reason. This word is reason here, and we were asking, okay, why is reason chosen? Because we're visualizing the attention scores, the weights, and we're seeing dependencies, retrospective, or into the next future, what word would be the next one. That is the idea of what we can visualize here. And to get a feeling, okay, if I, for example, use the word reason, then it's obvious that we have many possibilities in which directions can be. And if we then combine these words, then we have a strong center where context awareness would be there. So that is the idea, and different layouts. Just for an example, no real evaluation which layout fits best. It's just for the case that it can be visualized. It is a point in the future where we should look at, and for sure, as I mentioned before, we should know what parameters are we visualizing. That was the first thing. So concluding remarks are therefore that, as I mentioned, it was a student work, and we worked from behind with our student Raphael. And maybe a few of you have heard about Tamara-Wurzel's nested model. So it's kind of a meta level where we are located in the process of a project. We are here on the algorithmic level, so it's more or less testing, let's say. And as an example, we used the transformer model in the context of explainable AI. So, as I also mentioned, visualizing is the communicating fact or communicating factor. So I hope with this talk I got you an idea how the on vogue AI systems, for example, ChatGPT, are working in the end, because they are just looking for the next thing in the context. And that's also the reason, it's a nice fact, you maybe have run into that issue. If you use ChatGPT, for example, and the context is getting bigger and bigger, at some point, the model is not anymore able to refresh the context, because your model is so large that you are not able to focus on the entire set, and some things are cutted. So You're just looking at a small slice of that. That's the reason why these models are growing, and yeah, it's very, it's the future, but I would guess, and I think Daniel is also agreeing because he's also in our group there, we need to understand what is happening there, and we have to try to monitor, to visualize, to whatever in that context to get an idea what should be next. So homework, attention is not explanation. That's the reason why we have done this, because we were seeing it is necessary, but we need more exploration in this area. So that's it. Thank you. Open for questions.
I know some language models, they say that each gate could sometimes represent a different aspect of language. For example, some could capture the relationships in terms of like adjectives and a noun or adverbs and so on. So have you considered looking at the attention mechanism across each gate of the
Yeah, definitely. That's a next step. That's the component which I called here magic. So this stuff which is doing some weighting or some context awareness or some grammatically structured sentences. That is on the agenda, but not part of this journey here.
So thank you. So now we can go to the next presenter. It's Wagner Morris Diaz.
Yes, it's me.
Okay. With a paper entitled Evaluating Coding Approaches for Software Unit Testing Development.
Okay, this one.
Okay.
This one? Yes. Okay.
So,
Okay. So, my name is Tamir. I'm a professor from Federal University of Rio Grande do Norte. I'm going to present my paper titled Evaluating Coding Approach for Software Unit Test Development. Actually, this was a very good problem we had. We had a project which was demanded by a company in Brazil that provide credit card machines, and they needed something to improve the software quality of their product. So when we analyzed what they had, we saw that they don't have unit testing. So that was a problem that we tried to address on the first time. So we know that this increase of rapid demand of software tests of software demands better quality of the process of development. This is part of software engineering. And one of the approaches that we use to that is unit testing. That is trying to test a piece of a part of the code with the idea of the unit that should demonstrate that the program meets the requirements set in the design specification. When we started to understand that code and saw that we need to build this unit test, I know that's not the right process. Actually, the developers should build the unit test, but they have to do that because they had some functional testing, but the quality of that cannot be assured by all the units that they have using tools such JUnit. So we identified two approaches that we could use for the creation of this unit test. That was a function-based test. That is the most common that we use at JUnit. That is the method and the test. And there was also another one that we call the matrix-based test, that you can do one method and build many parameters and call many things by this matrix-based test. So to perform this evaluation of these approaches, actually these approaches, they was born from a discussion of our team We have developers that used to like more the function-based testing. The other ones like more matrix-based tests. So we decided to understand which one was the best one considering our scenario of the machines. So to perform the evaluation of these approaches, we use unit tests developing two industrial scale real-world software, a platform of health data management system, and a mobile device application that is responsible for financial transactions. These applications were embedded on these machines that the company produced. Something about unit testing, that is the process of test units, as I said before. When the test will send the inputs to indicate the expected output according to them. This is trying to just write the test and then check the outputs based on the inputs and the requirements. To write unit tests, either black box or white box methodology can be used. When you have white box, you see the code, you can do some coverage on the code. When you use black box, we don't see the code embedded there. We also use the Unity, which is the open source framework that allows developers to build unit tests for programs developed with Java. We also try to find some related work regarding this issue. We find 4 articles that used to compare automatic with manual unit testing, result of the automatic tools to achieve some scores of testing of coverage of the applications. We also find works that compare ad hoc individual unit tests with systematic automatic unit tests. With the systematic automated unit tests, you can decrease more than 20% in defects of the software. That's some results that you can find on these papers. We also find some papers related to optimization of code coverage, focus on high quality of the test data, something related to software quality also, the coverage. And these papers also present some strategies related to that. For example, TDD, code coverage, mutation score. So there was something that was always on these papers. But no one of them compares some approaches such as that I presented before. The process overview that we performed was design based on the requirements, implementation, and execution of the test. And this was the process that we built every one of the tests. We also do a design strategy. At that design stage, to design the test, we use the black box test methodology of equivalence partition and a boundary value analysis. That was because on these machines we have access to an API, but we didn't see the code of that API, that implementation, because actually they had an SDK, and there is a layer division that you can see what actually is implemented on this SDK. At the implementing stage, we use these JUnit APIs to implement the unit tests for these two approaches based on the planning of the previous stage. We actually try to understand, design, and then we pass to the implementation. That was the stage, documentation analysis. We have to understand what is on this actually requirements. This was a difficult process because it is financial application, so it's not an easy test. There are a lot of security issues and everything. We also define the equivalence classes based on the parameters, and then we define the limits of these values. Something important about these approaches that we were able to write the unit test, and then we created a tool to do this test on the machine, on the credit card machine. At stage 2, we implement the test case, verify the test execution, and refactor to the other approach that was actually before function-based and later matrix-based. That's what we call function-based test writing. As you can see there, we have function and a test, the main concept of unit test. And the developer needs to implement any test methods they need for each unit they want to test. And the matrix-based test, they can create one method and then create a matrix that will call and pass as many parameters as they want. Okay. So when we implement that, we try to evaluate which ones was the best approaches. For that, we decided to work on two different applications. One of them was a computational platform already consolidated in production for 3 years, which we implemented 433 unit test cases using both approaches. It was important to test each approach. It's a kind of experiment we did. And also a mobile application related to financial transactions of a point of sale terminal and highly used in the market, where we implemented 1,014 unit test case using both approaches. We actually wanted to verify each approaches, so for different kind of applications, we try to replicate the scenarios. For the evaluation, we focus on 4 aspects of unit test. For example, execution time required, execution memory required, test case traceability, scalability of write new testing cases. And then for that, the execution environment was a computer with i7 and 16 gigabytes of RAM and a point of sale that was running Android operating systems version 9 and 2 gigs of RAM. So in the health data management system, we have some numbers of line of codes. We can see that the function-based unit test approaches increase the number of line codes. The matrix-based does not. This is something related to the main characteristics of how do you write the tests. The time of execution, you can see that the function-based also demands more time for execution. And the matrix-based doesn't. But in terms of process memory, you can see that the matrix-based used more memory. That was something important for us because we have some restriction on the machine, the little machine, the credit card machine. So that was something that we observed on different scenarios. Even the web system. On financial mobile application, you can see that the line of codes of function-based was higher, really higher, because here we have interaction with JNI to access the API of the codes by the SDK. And then in the time of execution, they kind of perform almost the same, but in the process memory, the matrix-based approaches uses more memory. So that was something that we did not implement in this case because we know that we have a lot of restrictions regarding the memory of the machine. So that was important to us because we were able to choose what was the best case for the scenario of this project. And the unit test is now implemented on these machines. And then we also developed an application that can run this diagnostic, we call diagnostic tool, that execute all these 1,000 tests by a simple command or a simple application installed on these machines. So this work represented these two approaches to write unit tests. We called function-based and matrix-based. A set of 1,147 test cases was implemented in both the approaches to compare and evaluate that in terms of time of execution, memory, lines of code, scalability, and traceability. So to summarize that, we have that in terms of time execution, we have matrix-based is a better call. In terms of memory, function-based is a better call. In line of code, matrix-based is also a better call. In terms of traceability, the function-based is easier to find what unit you are testing. In terms of matrix-based, no, because you have many calls inside of a function. In terms of scalability, we don't actually have enough material to ensure that one approach is better than the other. So we need more study on that. The scalability of the two methodologies is the one aspect that we don't have sufficient evidence to conclude which is the better approach. As future work, we intend to carry out the experiment involving different test scenarios, include different applications. But in terms of our application or demand of the company that contract us, we also we actually work on function-based unit testing. So that's it. Thank you very much.
Thank you very much, Anthony, for your presentation.
I have one question related to the, you showed some metrics. Do you have a metric related to the effectiveness of the code, the quantity of the facts?
Good. That was something that we want to provide, but actually, as they doesn't have any kind of test, so we could actually extract something related to that. But maybe to the next version of the application they will have, because yes. But was really interesting for us because it's the biggest company that sells point of sales, and they use solutions that doesn't have unit testing, for example. Have some interaction with China and some suppliers, and that was something that we got. Oh God, that's not that's very risky.
In the case of financial transactions, do you use it as bank transactions or financial markets like
Credit card transactions.
Credit card.
Yes, actually, it was a credit card machine that you can approach the card and make transactions.
And in the part of the first stage, the analysis of documentation, what documentation you analyze?
Oh, nice. They have some documentation regarding the SDK they have, because they have some hardware there that implement, for example, contactless and something like that. And there is also an API that connected to the Visa and MasterCard. And then you have to understand all this architecture. But we worked always with an API that the provider, the supplier provide to them to create the applications. And that was the documentation, try to understand all the architecture. So thank you very much.
So now is the last presenter of this session. Is Luciana Rebello with a paper MOMS, an extensive platform for model transformation. Okay. Which is the first one?
No. The second.
The second? Okay. No?
No.
No? Just a second.
Maybe this one? No, it's not.
This one? No?
The
This
last
one?
No.
No?
I don't know one.
Maybe in another.
It's a new. Is it new?
Yes, this is the new.
We saw that?
This one? Okay.
Yes.
Okay. Just a second. So Luciano will tell you.
Okay. Is it clear?
This is just.
Good afternoon, everyone. I'm going to present this work, an extensible platform for model transformation. I'm Luciana Ribeiro from the Kansas Science Institute, and also I have a position on the Federal Institute of São Paulo. And this work was developed together with Gil Beckenbrock from the Federal University of Santa Catarina in Brazil, and also with Nandamude Vijay Kumar from the Brazilian National Institute for Space Research. So here, this work was started in the context of a critical system. More specifically, we work with the space and satellite software. And in this environment, as we have to deliver a very quality artifact, we use a lot of tools, a group of tools
to achieve the desired quality and the reliability for the software. And each one of these tools, they are designed to satisfy some specific shortcuts. And most of the time, they are not very complete and accurate. In that way, we should use complementary tools to achieve what we need, the high quality. And these tools, normally they make use of models which are stored in different formats. So this is an obstacle for us because we have to every time to remodel most of the time the same features of the system. And then we saw that it would be very useful if we could have an exchanging of models so that starting from a single model, we should achieve different formats and to perform the simulation, testing, validation, and so on. And this would save development timing and in addition to reducing the errors, because we should not be remodeling all the time. And but one thing that we wanted in that time is not to change very much the tools that the group are used to, because it would be difficult to do this change. And also we want a single place to store and manage all the projects that are developed by the group. In this manner, the proposed approach was the development of a model-oriented management system that we call MOMS, which is a microservice-based platform for the storage and transformation of models in a single place. So the main feature here is that this platform allows a transformation chain that is, we have a format and we can achieve in different formats. And also that these tools, they act in this platform as services. So if I have one kind of model, I can simply call a service and have this transformation. And this is the idea is that this adding a new tool, a new service, should be very flexible and not too complicated in order to make a lot of changes on the tools. And we started with two complementary tools that are very important for the group. The first one is called the Web Performance Charts, and it allows the generation of black box testing and also performance evaluation. And for this tool, the input is a performance chart, a state chart model, and the output, the tool makes a lot of transformation until we have a field state machine. And from this point, we can choose two ways. The first one is working with the performance evaluation. So here we can add the probabilities for the transitions and calculate the steady state probabilities. And the second possibility is to generate test cases once we have the finished state machine and have some criteria that can implement this test case generation. The second tool was more related to formal verification. It is called XPix. And here, once we have UML diagrams, we can perform model checking. At this stage, they work with only behavioral diagrams, such as activity sequence and behavioral state machine. And the transformation is performed until we have a transition system, and then the input language of this model checker that we are using, which currently is a new assembly. So the idea is starting from these two tools to start the new platform in a flexible way, and that in the way that should be scalable also to insert new tools. And the platform provides an API that can communicate it, with the user using graphical user interface. And here we can see all the tiles that we have in this platform. So here on the bottom we can see the services, and on the top we have the user interface. And on the right side we can see all the functionalities for the administrator that can maintain user, maintain services. So every time that I want to add another service, this is performed by the administrator. And also we have some dashboards related to some metrics and KPIs. And here on the left we have the functionalities for the user. So they have to be a profile. We have to register the user. They can also manage projects as well as groups. And here we have the API that makes the communication with all the tiles. And here we have the manager for user and permission tiles. That manages the users and as well as the permissions. And here we have the service manager tile responsible for which services are available on the platform, as well as the queue of services. And here the model tile, which manages all the models that are available on the platform. And here, the last, we have the project manager that make the management of the groups. And here are the main functionalities. So the platform is able to register users in these distinct levels of access. So we have the administrator, we have the individual, we have a member if this individual is member of the group, and we have also a manager that manages some groups. And the main functionality that this platform is able to load and download and deletion conversion of several types of model. So if I have an UML model, I can call a services that generate me a finite state machine, let's say, or a transition system. And these models and conversion sequences, they are grouped in a project. So every project will be, we can see the models that are available for this project, as well as the sequence of conversions. And these projects can be publicly approved, and they can be shared with other members of the groups. And each project is labeled with a list of tags, which are the characteristics of each project. So if I wanted to see which projects use a state chart, it's a way that we can find the projects in an easier manner. So here we have some prototypes. This work is an ongoing work, so we have only the front end that is developed, and the back end is almost an ongoing project. And for example, once the user is logged, we can see each one of the projects that belongs to this user, the description and the tags. And the user can download this project as a zip file, can copy, and so on. Here also we have which are the sequences that are available for this for this project. Also, we can copy and share the sequences. And here we have the project and the sequence that we can use to perform the transformation. Once we choose, we can click on that button and start the conversion. And here is one example more related to non-functional requirements, where we see the dark and the light screens. So here our idea is to present this architecture for model transformation. It's a platform intended to be extensible and scalable in order to add another tools and services. Future work includes the complete implementation to show how is the effectiveness, and you hope that this could be use it and be free for who wants to add the and make these transformations. Thank you.
Thank you, Lucia. There is no question, so
Thank you.
thank you all for attending this session. I think it's concluded, and we see you all together in the evening at the welcome party at 7:30. So thank you again.